Guys, welcome to the next video for Calc 1000. The plan for this video is to go through two sections that mechanically, in terms of doing the calculations, these sections aren't particularly difficult. The calculations themselves are straightforward and easy to do, but conceptually this is fairly challenging. There's a lot of leaps we're going to make. Here we go. So in the first of the two sections today, in section 5.3, we're going to tackle the fundamental theorem of calculus, or part of the fundamental theorem of calculus, or several parts of this. The construction we're going to work with assumes the following: that we have a function that's continuous on the interval between x is equal to a and x is equal to b. So there's some part of the number line over which the function of interest is continuous. And the function that's continuous is labeled f of x, or f of t, or f of whatever the variable is. We can define a new function, g of x, as an integral from a to x, so lower bound a, upper bound x, of f of t dt. So this integral, this part on the right hand side of the expression, is how we were constructing the area under a curve. So from section 5.2, where we were drawing a correspondence between areas constructed with the rectangle method and areas that are constructed as integrals. Okay, and this new function that we're creating this way, g of x, is also going to be continuous between a and b, and it'll be differentiable between a and b. Now, what the fundamental theorem of calculus says, so part 1 of the fundamental theorem, and I'm going to denote that FTC1, is that the derivative of g is equal to f of x. So if we're taking the derivative of the antiderivative of f of t evaluated from a to x, what we'll get is f of x. Now what this statement, I'll put this in words, so d by dx is the derivative of what comes next is the antiderivative of f of x is giving us just the original function. So the derivative of the antiderivative gives us the original. It's almost an inverse function property. But they're not functions, it's an inverse property. It's an inverse operation property, that the derivative is the opposite of the antiderivative. One undoes what the other one does. We're going to explore that concept, that inverse function property concept, and examples in a bit later in the video. But for now, let's take this statement at face value. We'll take it as almost a definition. But it isn't, but we'll take it as if it is a definition, that the derivative of the integral from a to x of f of t dt is just going to be f of x. If you wanted to see the full proof, it's in the textbook. I have to warn you, the construction of the proof is somewhat convoluted. I don't really like the proof that's in the book. In these notes, I'm going to provide a little more of an intuitive proof, but the intuitive proof I'm going to show isn't really complete and isn't formal. It's more of a visual proof. And the one in the book uses the squeeze theorem, whereas the one I'm going to show you doesn't use much else other than the definition of the derivative, in fact. Okay. Now, this function that we created, this g of x function, how exactly is it related to f of t? So recall from the previous two sections, 5.1 and 5.2, that the integral from a to b of f of x dx gave us the area underneath f of x from x is equal to a to x is equal to b. Now we don't have a top bound here that's a constant. We have a top bound that is a variable. So if we think about what that does, say that we're the f of t function is given in blue here, so that's f of t. We have the t-axis going left to right, and we have the y-axis going up and down. Say that our a value is -4, just to match the picture that's here. We're looking for the area underneath this curve from t equals -4 up to some particular value of t. So maybe we could treat that upper value of the integral, that upper bound, as a slider. We can slide it back and forth, left and right. And if we slide it to the left, we make the area that's under the curve smaller. If we slide it to the right, we make the area larger. And that's what the pictures are indicating, going from the top to the bottom. It's taking that upper bound, which we're calling x, and making x larger and larger and larger. So what we are creating is a function of the area. An area function that's a function of the upper bound. So as we change the upper bound, the total area that's enclosed under the curve will also change. You could think of this as how much area do we have so far, up to a particular x value. So it has a physical interpretation. There's something we can get out of it. Here's my visual proof. It's not really a proof, it's more of a motivation for the fundamental theorem of calculus. The construction of this proof begins and ends with a picture. I'm going to have my t-axis, my y-axis, and then a function. Doesn't have to be any particular function, but it does need a picture. So I'm going to say this is y equals f of t. And there's nothing special about the choice I'm about to make, but I'm going to start the lower bound at 0. It makes some of the steps easier for the visual proof I'm going to show you, but you don't need to do that. We're going to start at t is equal to 0, and we're going to end at t equals x. Okay, and then that area, I'll shade that in. That's the area that we're after. I'm going to give it a name. I'm going to call it a of x. It is a function of whatever x, like whatever number we plug in for x. If we increase x, the area will be larger. If we have a small value of x, the area will be small. Underneath this picture, I'm going to do my best to make a copy. So it's the t-axis and the y-axis. I'm going to do what I can to get the same function there. So there's y is equal to f of t. And we're going to do from t equals 0, but we're going to go a little bit further to the right. We're not going to stop at t is equal to x. We will stop at t equals x plus a little bit. I'm going to call the little bit h. Okay. Actually, I'll do it this way. Okay. So we're going a little over to the right, and you may be able to tell what I'm about to do is This area function is a bit different. It's a bit more than the first one. So this area function is going to be the entirety of it, the whole thing, total area, from x equals 0 to from t is equal to 0, sorry, from t equals 0 to t equals x plus h is the yellow shaded part plus the red shaded part. Now, this a of x we saw from the previous section, from 5.2. A of x is equal to the integral from 0 to x of f of t dt. Now this area we have down here, which I'll write in red, a of x plus h is integral from 0 to x plus h of f of t dt, which isn't, this construction of it isn't going to be very helpful. So I'm going to do an approximation. I'm going to say it's approximately equal to the yellow area So the yellow area is a of x plus the extra bit. Actually, I have to be careful with my color coding. Don't want to make it red, make it purple. So area of x plus h is equal to area of x plus the red area. And I'm going to make an approximation. Instead of saying it's exactly equal, I'm going to say it's that yellow shaded region plus a rectangle. And think back to section 5.1, how we calculated the width and the height of the rectangle. So we have a of x plus base times height well, the base, the distance we're traveling in the x direction, we're going from x to x plus h, so the base is h, and the height we get by evaluating the function either the left or the right endpoint of the rectangle. I'm going to pick the left endpoint. I'm going to say it's the value of the function at x plus h, or at x rather, f of x. So a of x plus h is approximately equal to a of x plus h times f of x. I'm going to take that result, continue with it up here. We have a of x plus h is approximately a of x plus h times f of x. Let's rearrange this. What I'm going to do next is I'm going to subtract a of x from both sides. So a of x plus h minus a of x is approximately equal to h times f of x. Then I'm going to divide both sides by h, and we get f of x is equal to, or approximately equals, a of x plus h minus a of x all over h. Now let's go back to the approximation. This is an approximation because this little extra red rectangle area is missing some of the area underneath that curve, or depending on the curve, it may contain extra area compared to the real area. We can make it exact. We can get rid of the approximation by taking the limit as h approaches 0. So I'm going to say f of x is equal to the limit as h approaches 0, since the difference is going to be infinitely small between the real area of the rectangle and the real area that's shaded in red and the approximating rectangle for that region. So limit as h approaches 0 of a of x plus h minus a of x all over h. And you've seen that before. That's the definition of the derivative. So f of x is equal to dA by dH, the derivative of the area function, dx, sorry, dA by dx, the derivative of the area function with respect to x. Now we can integrate both sides of the expression. So integral of f of x dx equals integral dA by dx with respect to x. So multiplying both sides by dx and then integrating both sides. So integral of f of x dx equals what are we doing? Okay. Hold on. Sorry about that. Let's not do that. Let's use the statement that we have up above. So this is d by dx of, up above it says that a of x is integral from 0 to x of f of t dt. So I'm going to recycle this. And that's the fundamental theorem. Sorry, I was tangling myself up in knots. I was about to attempt to prove the other direction in the fundamental theorem, which we're not doing right now. So f of x is equal to d by dx of the integral from 0 to x of f of t dt as needed. It's kind of a hand-wavy proof, but I like it. I like it because it's based on pictures. And it takes us back to the definition of the derivative. Okay, and that was the goal. We wanted to say that f of x is equal to the derivative of the antiderivative from a to x of f of t dt. That's exactly what we did. And that 0 isn't special. That could be any a value and the answer wouldn't change. Okay. So at this point we're going to use this as a formula. We're going to say if you have an expression given by an integral, so here we have an expression g of x is equal to the integral from 7 to x of 2t dt. And you're asked for the derivative of that expression, so we're asked for g prime. G prime of x is going to be d by dx of the integral from 7 to x of 2t dt. This is just going to be equal to 2x by fundamental theorem of calculus. And that's it. And look at what that formula we have on the previous slide is. We're taking the antiderivative from 0 to x of f of t dt, and we just get f of x. We're replacing the t with an x. That's what the formula says to do, and that's all that I've done here. I've replaced the t inside the function. So here our f of t was 2 times t. And now this is just f of x. The t replaced by an x. Okay, let's do another one. We're given g of x. We want g prime. So g prime of x is going to be the derivative d by dx of the antiderivative. Antiderivative from 3 to x of the square root of that stuff, e to the 5t plus t squared dt. And then by the fundamental theorem, this is just going to be the square root of e to the 5x plus x squared by FTC. So here, f of t was the square root of e to the 5t plus t squared. And our answer is just f of x, the t replaced by x. Now this can be generalized. I don't want to go through the proof of the generalization. It is essentially a statement of the chain rule with the fundamental theorem, and it states that if you take the derivative of the antiderivative of f of t dt, but the bounds are not a constant to a variable, instead they're a constant to a function, so integral goes from t equals a to t equals h of x, then what you'll get is instead of f of x, you get f of h of x, and you have to multiply by h prime. So it has the same structure as a chain rule. It has that multiplication by the derivative of the inside, and here the inside isn't really the inside, it's the upper bound of integration. And really this is just a fundamental theorem with a chain rule. That's what this is. This is something you can treat as if it's a formula. You can treat it as something that is, you memorize it, but it isn't different than what we just did. So let's see how it works. We're going to revisit a similar looking function. G of x here is the integral we get from integrating from 7 to x cubed of e to the 5t plus t squared all inside a square root. So g prime of x, the thing that we're after, it's asking us for g prime, so that's what we're going to do. We're going to take the derivative of this, d by dx, 7 to x cubed of the square root of e to the 5t plus t squared. Well, I'm going to make sure I put my dt. Yeah, I did. Okay. So I'm going to label these pieces here that f of t is the square root of e to the 5t plus t squared. And h of x, go back to the formula, the top bound we called h of x if it's a function, is x cubed. And what we'll get from the fundamental theorem is f of h of x times h prime of x. From FTC formula with chain rule. So without the chain rule, it's just f of x, but with the chain rule, it's f of h of x times h prime. So we have f of, we can dispense with that. We have the square root of, not e to the 5x, but e to the 5 times h of x plus h of x all squared multiplied by the derivative of x cubed, which is 3x squared. Okay, now I'm going to plug in what h of x is. We have e to the 5 x cubed plus x cubed all squared times 3x squared. And then use exponent laws to simplify x to the 3 all to the 2. We have a power to a power, the powers multiply, so e to the 5x cubed plus x to the power of 6 times 3x squared. And notice what is coming out of all of these, that these are functions. We're getting function of x that is extracted from this operation, from this procedure. Okay, another example. We're asked for g prime, so I'm going to take the derivative of the antiderivatives, d by dx, integral from 5 to the sine of x of t squared dt. Okay, so here our f of t is t squared, and our h of x is sine of x. So according to the fundamental theorem, we're going to get f of h of x times h prime of x by fundamental theorem of calculus. So we have h of x squared, since we're replacing the t with the h of x, multiplied by h prime, so multiplied by the derivative of sine of x, which is cosine of x. Okay, so sine of x squared is sine squared of x times cosine of x. That'll be your answer. Okay, next one. This is different. In the previous examples, our lower bound was a constant, and now our lower bound is also a function. Now I'm going to use a trick. I'm going to use the following integral property. Recall, so this was the last thing we did in the previous video. We went through some integral properties, and we didn't prove all of them. We motivated them with pictures. So geometric motivations. Recall that the integral from a to b of something can be written as the integral from a to c plus integral from c to b. And the c just comes out of nowhere. You make anything up that you want. Say that we're integrating from 0 to 10. Well, you can take a break at 3. Do an integral from 0 to 3, and then plus integral from 3 to 10. So I'm going to use that. We're not taking the derivative yet. I'm going to split this up as the integral from ln of x to something. So you pick something, like 5 or 2 or 0. I'm going to pick 0. I feel like picking 0 today. Maybe if I was doing this video tomorrow, I'd pick 2 or 7 or something. E to the t dt. Be careful with how I draw this. Plus integral from 0 to 2 ln of x e to the t dt. Now the next rule I'm going to use was that the integral from a to b can be written as the negative of the integral from b to a. So these are from last time, from the last video. Okay, I'm only going to use that on the first one. I'm only going to use that in the first integral. So equals negative integral from 0 to ln of x of e to the t dt. The second one I won't change, integral from 0 to 2 times the ln of x of e to the t dt. And now I'm going to take the derivative. Now I'm going to find g prime. So this is g of x. Now g prime is going to be negative d by dx. We have the integral from 0 to ln of x of e to the t dt plus d by dx, so taking the derivative of the second piece as well, integral from 0 to 2 ln of x of e to the t dt, and then use the fundamental theorem on both pieces. So here we'll have e to the ln of x multiplied by the derivative of ln of x, which is 1 over x. Oh, forgot the minus sign. Plus e to the 2 ln of x times the derivative of 2 ln of x, which is 2 over x. And that was from FTC. So recall the FTC formula from the last example. If we're taking the derivative d by dx of the integral from a constant to a function, so to h of x of f of t dt, what we'll get is f of h times h prime. So each of these is f of h, e to the t evaluated at ln of x, so e to the ln of x times h prime, so times 1 over x, since 1 over x is the derivative of ln of x. And the same for the second piece. We can simplify these. This is negative x times 1 over x using the cancellation law. Next one, we need to work on a little bit more than that. We can't cancel the e and the ln, but we can bring the 2 up as a power using the log property. 2 times ln of x is the same as ln of x to the power of 2. And we still have multiplication by 2 over x outside. Okay, now we can cancel the e and the ln. Okay, the first piece we have negative x times 1 over x, we get negative 1. In the second piece, we get x squared times 2 over x, which simplifies, we get negative 1 plus 2x. That's our answer. -1 plus 2x. Was a hard problem. I'm going to give you a shortcut. It's a formula that builds in those two antiderivative or integral properties that we used inside solving this problem. So you want to build it all in together. Then the integral, or I have to be careful, the derivative, d by dx of the integral from say k of x to h of x of the function f of t dt So if you apply those two properties to this expression directly, what you'll find is that this is going to be f of h of x times h prime of x minus f of k of x times k prime. And I recommend making a list of formulas like these. So having this shortcut written down somewhere, so when you're doing your final exam or when you're studying for your final exam, you're able to attack questions that look like this more quickly. It's not a bad thing to have formulas, as long as you know where they come from. Okay, so I'm going to use that. It's worth writing down again. We will use the fact that the derivative d by dx of the integral k of x to h of x of the function f of t dt will be equal to f of h times h prime minus f of k times k prime. So again, we start by taking the derivative since we're after g prime. G prime is the derivative of the right hand side, d by dx integral from negative x to x of t squared dt. And the fundamental theorem up above says that this is going to be x squared multiplied by the derivative of x, which is 1, minus negative x all squared times the derivative of negative x, which is negative 1. So directly using the formula that's up above, I'll label the pieces here. So this has f of t equals t squared, has h of x equals x, and k of x equals negative x. So that's the above formula with those inputs. And if we simplify, we get x squared, negative cancels, plus x squared, we get 2x squared. Okay, that'll be our answer. Right, next one, next example. Nothing much has changed. We're going from negative x to x, but instead of t squared, we have a t cubed. Okay, so g prime of x is the derivative, d by dx, integral from negative x to x of t cubed dt, which according to the special case of the fundamental theorem, with the chain rule, the top and bottom bound of both functions, we get the function t cubed evaluated at x, so x to the 3, times the derivative of x, which is 1, minus the function evaluated at the bottom bound, so negative x to the power of 3, times the derivative of negative x, which is negative 1. And we get x cubed minus, we have x, negative x to the power of 3, which is going to be negative x, multiplied by negative, so it's still going to be negative x cubed. We get 0. Even versus odd integral properties. So I think it's a bit early for me to write these down. Certainly, these two examples don't constitute a proof of these statements I'm about to write. So this one, integral from negative x to x of t squared, and integral from negative x to x of t cubed. But you may be able to convince yourself of the validity of these statements. The first one is, if we're integrating from minus a to a of an odd function, what we'll get is 0. So odd functions are like x, y equals x is an odd function, y equals x cubed is an odd function, y equals x to the power of 7 is an odd function. And the second property is, if we're integrating from minus a to a of an even function, we won't get 0, we'll get 2 times the integral from 0 to a of that even function. Again, these two examples don't prove these two properties, but they're definitely properties of integrals. And they're consistent. They're consistent with the examples that we just saw. So this example on the left here in purple, this is an odd function evaluated on symmetric bounds. We're going from negative a to a. And the answer came out as 0, whereas the first one, if we think about what the integral from 0 to x of this thing is equal to, it's x squared. Well, this is just 2 times that. And this is an even function that we're integrating. Well, it's kind of an aside for now, but this is sometimes the only way to solve the problem. I'm going to put it in quotes. Because it's not ever going to be the only way. It'll be the only way based on what you've learned so far. And I think in life, whenever anyone tells you this or that is the only way to ever do something, this is the only way you can do it, and there's no other way possible, you should always interpret that as a lack of creativity. Nothing more. Because there's never only one way to do something. There's always many ways to do something. Okay. That's the end of 5.3. part 1. 5.3 part 2 takes on a different flavor. It's still a fundamental theorem, and the statement of the fundamental theorem here is different. The function of interest, the function f of x, is still a function that we'll say is continuous between x is equal to a and x is equal to b. And we'll call capital F, so lowercase f, we're making a statement about the requirements of it. Uppercase F, capital F, we'll call the antiderivative of little f. The fundamental theorem of calculus part 2 states that the antiderivative of little f of t dt, evaluated from t equals a to t is equal to b, is going to be the antiderivative at the top bound minus the antiderivative at the bottom bound. This might look like a rule that we already wrote down today, and it's no accident. So as an example, integral from, let's say, 1 to 4 of x squared dx. I'm going to use x's instead of t's. Doesn't matter what the variable labels are. Labels are interchangeable. Is going to be the antiderivative at b minus the antiderivative at a. So let's get that antiderivative. So capital F of x is going to be the antiderivative of little f of x squared. And we saw from 4.9 on antiderivatives that there's something called an anti-power rule. The power goes up by 1, you divide by the new power to take the antiderivative. So 1 over 3x to the 3 plus c. I'll include the plus c, even though later on we'll recognize it isn't necessary. Okay, so this is going to be capital F at 4 minus capital F at 1. So we have 1 over 3 times 4 to the 3 minus 1 over 3 times 1 to the 3. Oh, I gotta be careful. Let's put the plus c as well. Plus c minus, now f of 1, we get 1 over 3 times 1 to the 3 plus c. This is why I didn't write the plus c. I already know how the story ends, but you don't know how the story ends yet. The c that we get from the first part cancels with the c we get from the second part. Okay, and then we can simplify. 4 to the 3 is 64, so 64 over 3 minus 1 over 3. 1 to the 3 is 1. So that's 63 over 3. If it was 60 divided by 3, the answer would be 20. We have an additional 3, so the answer is 21. Now, one of you asked an email in the notes for 5.1 when we were doing integrals the nasty way, or when we were doing areas the nasty way with rectangles, and off in the corner in some of the examples I had this calculation where I was getting the answer in one line or 2 lines. I asked, can you show me how to do that? I really want to know how to do these quickly. Well, here it is. Those little shortcuts I was taking to confirm that the answers that we were getting in class were correct was the fundamental theorem, was the connection between areas and antiderivatives, which is what this is saying. Now, I have to go back and recall that the integral from a to b of f of t dt is identifying the area under the curve of f of t from t is equal to a to t is equal to b. And that means when we're calculating areas under curves, we could go directly to antiderivatives. So that's the massive shortcut. And that's one of the reasons why there was such a fuss. There was such turmoil, good turmoil mostly, when these properties were originally being explored. As we go through, and as you look at notes and resources and other people's videos online, there's some notation that pops up when we're doing these types of antiderivatives. The evaluation f of b minus f of a, so the antiderivative at the top bound minus the antiderivative at the bottom bound. The evaluation notation, so taking the function capital F of x and plugging in a number, plugging another number, and subtracting, that's indicated on the right hand side of the slide here. At capital F of x with that vertical bar line, a at the bottom, b at the top, means capital F evaluated at b minus capital F evaluated at a. So an example. Say we had sine of x evaluated from 0 to pi over 2. What that means is this is sine of the top bound, sine of the top number, minus sine of the bottom number. Minus sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. So we get 1 as the answer. I'm showing you this just to highlight notation. That vertical bar means evaluate and subtract the two results. Okay, also, in addition to that, you'll notice as you go through all of these examples that when you do an integral that does not have bounds on it, you will always get a function with, oh, it's not a good color, with plus c. Okay, you'll always get a plus c when you're doing an antiderivative without bounds. Whenever you have an antiderivative where the bounds are functions, or the derivative of the antiderivative where the bounds are functions, you will get a function as a result. So, and there will be no plus c. And if you're integrating a function and the bounds are both constants, going from a to b, if f of x dx, then what will come out is not a function, but what will come out is a number. Usually. Sometimes nothing comes out. Sometimes the expression doesn't have any meaning. But we'll save that problem for a different course. So that's what happens when the assumptions we had about continuity, in some cases, it happens when continuity is violated. In other cases, even though continuity is violated, we can get away with an integral like this. Depends on the type of discontinuity. Anyway, so let's look at some examples of antiderivatives with bounds of integration. And we'll solve them using the fundamental theorem, not using an area method, not using rectangles like we did in 5.1, but using antiderivatives. So my problem solving process is as follows. Step 1 is I want to find the antiderivative of the function. Which is capital F of x equals the antiderivative of sine of x dx. Okay. And the antiderivative of sine of x, recall what that means. D by dx of what equals sine of x. So what do you take the derivative of in order to get sine of x? And the answer is not cosine of x. Derivative of cosine is negative sine of x. We need to cancel out that negative sign, so we have to start with a minus. Okay, So that's the answer for the antiderivative. Now step 2. Evaluate capital F at the top bound minus capital F at the bottom bound. Capital F pi minus capital F of 0. So that's going to be, for the top bound, negative cos of pi plus c. And then for the bottom bound, negative cos of 0 plus c. So we get negative 1 plus c minus plus. Cos of 0 is 1, and minus c, the negative travels to the bracket. The plus c and the minus c destroy each other. Negative, negative, so positive 1 plus positive 1. We get 2 as the answer. Now imagine if the question said, find the area underneath sine of x from x equals 0 to x is equal to pi. You used rectangles, and you want to take the expression and inside the limit. The limit as the number of rectangles goes to infinity, but your heights of all the rectangles would involve sine functions, and there's no nice summation formula for those. So it's kind of miraculous that we can do a problem like this that is very, very challenging to interpret geometrically, or very not to interpret, but very challenging to complete geometrically, or by brute force with a summation formula. And it's relatively easy to do with this fundamental theorem. Okay, let's do another one. Find the integral from 0 to 2 of 6x squared dx. So step 1, find the antiderivative, which I'll call capital F of x. Six x squared dx. So the anti-power rule says that I take the antiderivative of x to the power of 2 by decreasing or increasing the power by 1 and dividing by the new power. So x to the power of 3 divided by 3. The constant in front just doesn't directly participate. It waits for the antiderivative to be completed and then comes back in and multiplies. So 6 over 3, we have 2x cubed plus c. And we know the c is going to cancel. Since we have bounds. So we don't need to write the plus c. Now step 2. Evaluate capital F at the top bound. Capital F of 2 minus capital F at the bottom bound. Capital F of 0. So we'll get 2 times 2 to the 3 minus 2 times 2 to the 0. Plus 2 times 0 to the 2. 0 to the 3, what am I doing? Replacing x with the number, not everything with the number. And then simplify. So 2 to 3 is 8 times 2 is 16. 16 minus 0. So we get 16 as the result. Okay, what I want to do underneath is write down standard notation. Because what is up above is not standard. It's my own kind of homebrew notation. But I like it. But most solutions are not written out that way. What we would do is we would say the integral from 0 to 2 of 6x squared dx. We would take the antiderivative the same way we did up above. Oh, I don't want all that. Equals. So 6 times 1/3 x to the 3 won't bother writing the plus c. It's going to cancel. Evaluated from 0 to 2. Remember that vertical line? Well, there's that vertical line. We'll clean this up a little bit. This is 2x cubed. Evaluated from 0 to 2. Plug in the top number. 2 times 2 to the 3. Plug in the bottom number. 2 times 0 to the 3. 16 minus 0. 16. So you end up saving writing. You save space, you save writing. It's the same answer. I'm going to do subsequent calculations this way. But if you find it easier to do antiderivatives with bounds using the method or the notations up above, please use the method above. There's nothing wrong with it. So it just isn't standard. It's not going to align with what you see in other resources. All right. A more complicated looking question that isn't, I mean, it is harder, but here we go. It's not that bad. Question is asking us to find the area of the region that lies below y equals secant squared x and above the line y equals 0 for x between 0 and pi over 6. So recall from 5.2 that the area is going to be given by the integral from a to b of f of x dx. So the integral from 0 to pi over 6, the function is secant squared. Okay, now we're asking the following question. D by dx of what gives you secant squared? And the answer is tan. The derivative of tan of x is secant squared. Okay, so what we're going to get is the antiderivative of secant squared, tan of x, evaluated, so vertical line from 0 to pi over 6. So tan of pi over 6 minus tan of 0. Special triangle, pi by 6, pi by 3, so smallest side, pi over 6 gets across from it the smallest angle, pi over 6 gets the smallest side 1, across from the pi over 3 is a root 3, Pythagorean theorem gives you hypotenuse 2, and then tan pi over 6. This is for if you don't have it memorized, but you do have your special triangle memorized. Tan pi over 6 is opposite over adjacent, which is 1 over root 3. So 1 over root 3. And if you think about the cast rule, the tan function is negative in the C quadrant, so negative for angles that are less than 0. Positive for angles greater than 0 since it's the A quadrant. So the function crosses from negatives to positives. That means in the middle it's going to be 0. So tan of 0 is 0. And we know it's and you also have to know it's continuous across 0. So be careful with tan using that trick, using the cast rule to figure it out, because it doesn't work at pi over 2, for example. Anyway, so we get 1 over root 3 for the area. We're going to do questions like this much more carefully inside section 6.1 because we took a lot of things for granted. I didn't even check, is this function always above the line or always above y equals 0 between x equals 0 and x is equal to pi over 6. Because if it's not, then we've got to be careful. There's more steps we have to do. There's more analysis we have to do when we construct the expression that represents the area under the curve. So it's kind of a preview. Okay, tougher examples. I know you guys hate these. Problems involving absolute value functions. Here we go. How do we do this? So a function, absolute value of x, is equal to a piecewise. It's equal to negative x for x less than 0. It's equal to positive x for x greater than 0. If I create 4 x to the 3 in absolute values, it's also a piecewise function. It's equal to negative 4x to the 3 for x less than 0, and positive 4x to the 3 for x greater than 0. So think about the x values that would require you to multiply by negative 1 to make the entire expression positive, and x values that you would multiply by 1 to make the entire expression positive. Okay, so see how it switches at 0? That means we're going to have to split our integral into two integrals. An integral from -2 to 0 and an integral from 0 to 3. So we're choosing 0 this time for a reason. The last time I split up an integral into two integrals, I just chose 0 because I felt like it. I could have picked 7. Nothing would have changed. Here, there's a reason why 0 is being chosen. Okay, so this equals the integral from -2 to 0 of the form of the absolute value function for x values between -2 and 0. So that's for x less than 0. So negative 4x to the power of 3. And then plus integral from 0 to 3 of the part of the piecewise function for x values larger than 0. Since we're going from 0 to 3, that's larger than 0, so 4x to the 3. You can simplify. Well, actually, you can integrate. The antiderivative of 4x cubed is x to the power of 4. I'll do it in steps. We have -4 weights outside, 1/4x to the 4. Power goes up by 1. We divide by the new power. That's evaluated from -2 to 0. Plus, same thing happens here. The 4 weights outside. We have antiderivative of x to the 3, which is 1/4x to the 4. Evaluated from 0 to 2. Okay, so we have negative x to the power of 4, evaluated from -2 to 0, plus positive x to the 4, evaluated from 0 to 2. Oh, 0 to 3. Sorry, my bound magically changed. It should not have magically changed. There is no magically changing of things. Okay. Now, this notation means we plug in the top bound. So negative 0 to the 4. Plug in the bottom bound. -2 to the 4. Plus, then we do the same thing for the second piece. We have a 3 to the 4 minus a 0 to the 4. Okay, so 0, and then we get 2 to the 4 is 16, and then those other two negatives destroy each other, so positive 16, negative times negative positive, plus 3 to the 4 is 3 times 3, 9 times 3 again, 27 times 3 again, 81. And that total answer is 97. So tougher problem. The antiderivative part was relatively straightforward. We use the anti-power rule and simplify. But we had to recognize how to split the absolute value function up into a piecewise. Then where the function changes dictates how we split that integral up, like what x-coordinate do we take a pit stop at, and then the rest is mechanical. All right. A test, a quick quiz for you to do on your own. So integral from -3 to 5 of the absolute value of x minus 1. And so I recommend pausing the video, getting out a piece of paper, and trying it out. Okay. Hopefully you paused for quite a long time, worked through it, and maybe you screwed it up. Maybe you didn't split up the piecewise function properly, or didn't treat the absolute value function properly. That would be the common mistake to make based on the last one, because this is not absolute value of x, it's not absolute value of 2x, or absolute value of 3x, or 3x cubed, or anything like that. It's absolute value of x minus 1. And when we split this integral up, our construction of the piecewise function is as follows. It's either going to be negative of x minus 1 or positive of x minus 1, and it does not switch at 0. It switches at 1. So it's the first one for x values less than 1, and the second one for x values larger than 1. So do a test if you're not comfortable. Like what? If you're asking why. Why is it switching at 1 instead of 0? Here's the test. So plug in an x value of let's say 3, absolute value of 3 minus 1. So absolute value of 2. You don't have to do anything to it. It's just 2. What if we choose a different x value? What if we choose negative 4? So negative 4 minus 1. The absolute value of negative 5. I cannot just drop the absolute value sign. I have to multiply by negative. Negative 5 in order to make it positive. So then you ask yourself, where does it switch? When I plugged in 3, I didn't need to multiply by negative. When I plugged in negative 4, I did need to multiply by a negative. What happens if you plug in 0 for x? Well, you get absolute value of negative 1. You have to multiply by a negative. What if you plug in 1? Plug in 1, you get 0, and you don't need to do anything. You just can leave it as the function. If you go below 1, let's say you go to 0.99, so 0.99 minus 1, you get a small negative number. To make it positive, to do the absolute value operation, you need to multiply by negative 1. So 1 is the special value where the function switches. Switches at x equals 1. And that is going to tell us where we have to split up the integral. Okay. So this is going to be the integral from negative 3 to 1 of the function that is the part of the piecewise function inside that region for those x values. So for x values between negative 3 and negative 1, that's for x less than 1. That means absolute value of x minus 1 is going to be negative x minus 1, plus the integral from 1 to 3, or 1 to 5 rather, 1 to 5 of the positive of x minus 1. Okay, we can take the antiderivative of each piece separately. Antiderivative of x is 1/2 x squared. Antiderivative of 1 is x. Negative times negative gives you a positive. And then we're going to evaluate this from -3 to 1. The second antiderivative of x is 1/2 x squared. Antiderivative of 1 is x. And we're evaluating this from 1 to 5. Okay, now let's simplify. Not simplify, evaluate. Plug in the top bound. We get -1/2 plus 1. Plug in the bottom bound. We get -9/2 minus 3. Now for the second part, we have 1/2 of 5 squared, so 25/2, minus 5. And then minus the bottom bound, 1/2 of 1 squared, which is 1/2, minus 1. Okay, and then simplify. So I'm going to put all the 1/2 stuff together. We have a -1/2, positive 9/2, positive 25/2, -1/2, and then add the integers together. Plus 1, plus 3, since negative times negative gives you positive, minus 5, plus 1. So we'll do it that way. Now, the denominators for the first four are all common. We can add them together. We have -1 plus 9, so 8. 8 plus 25, 33. 33 minus 1, 32. 32 divided by 2, 16. And then plus 1 plus 3, 4 minus 5. Something's up. Oh no, nothing's up. That's all going to cancel out. All 0. Plus 0. We get 16. So answer D. Hard question. What I really want to highlight inside this section is the relationship between derivatives and antiderivatives. We're exploring that relationship much more deeply now. That when you take the derivative of a antiderivative, you get the original function back, and when you integrate the derivative, you will also get the original function back. There's an inverse operation property between them, but it isn't perfect. It's not a perfect inverse operation property. If we don't have bounds, if we're just doing an integral of the antiderivative, or the integral of the derivative, we'll end up getting a plus c. So they're not perfect inverse operations. Okay, another kind of way to summarize this. What chapter 5 is about is areas under curves. Even though they're calculated in very different ways in the different sections, they all are about the same property. We started with approximations, different types of approximate approaches involving rectangles, left rectangles, right rectangles, midpoint rectangles. We turn the approximation exact by letting the number of rectangles go to infinity and having the width of each rectangle go to 0. For some types of expressions like that, we use summation rules, summation tricks, if you want to call them that, to get nice compact expressions for the area. Then I used a picture to motivate the fundamental theorem of calculus and connect it to the area under a curve. So that then gives a connection between these area methods using rectangles and antiderivatives. Everything here is connected. It looks like if you compare what we're doing mechanically in 5.1 to what we're doing mechanically in what we just did mechanically here, it looks so different. We're not doing sums, we're not doing rectangles, but it's the same. It's amazing. Okay, 5.4. I'll take a break on the videos, split it up into 2 videos, and post them together, because I think this is a long video. I don't want to have like a 2-hour posting on YouTube.